Hello, so I'm going to explain the problem number 3 of MEXT 2017 Undergraduate. So, this is the problem. So there's a hemisphere of radius r fixed on the horizontal floor with a small ball at mass m sliced down from the top of the hemisphere at point A with 0 initial speed. There's a ball. There is a ball m. It moves here with 0 initial speed. There is no friction, and after sliding in the surface, the ball leaves the surface of the hemisphere at point B. So it leaves at point B, then hits the horizontal floor at point C. So the position of the ball is described by theta. At this time, so as the ball goes on, it forms an angle of theta, and the acceleration of gravity is denoted as g. So we're going to number 1. We are asked to find the speed of the ball when the ball is at a position of the hemisphere described by angle theta. So what you have to know is that the conservation of the mechanical energy. So the potential energy plus the kinetic energy before is equal to the potential energy and kinetic energy after. So let's say that a ball here, a ball at point A, and ball at point B, and ball at point C, this always holds. So the mechanical energy, so U plus K is mechanical energy. So mechanical energy here and at A and mechanical energy at B is always the same. So the mechanical energy is always conserved in this case. So the potential energy is equal to the mass times gravity times height, and the kinetic energy is a half times m, the mass, times velocity squared. And the thing that you should know too is that when there is a circle and let there be a line, so this red line, it moves around the circle, so its tip is always at the circle, and it moves to the angle theta. At the angle theta, we can describe this length of the tip and the vertical line of the tip. So how we find it is that the adjacent line is the length of this line, that is r, times cosine theta, and the opposite of the angle of theta is the length of the radius of the circle times sine theta. So to find the speed of the ball, so let me illustrate it. So let's draw a hemisphere or a semicircle, and the ball moves from here to here, let's say here, and the semicircle has a radius of r. So notice that we can use the conservation of mechanical energy. So mechanical energy at this point is so we write the potential energy, that is mg times the height, and the height is r. The height from here to here is r, so is mgr plus the kinetic energy. But from the problem we know that uh, it slides down from the top of the hemisphere at point A with zero initial speed, so it doesn't have kinetic energy. It doesn't have kinetic energy here. So the mechanical energy at this tip is only mgr. So it is equal to the mechanical energy here. And so we search the potential energy. And the potential energy here is also the height of here of this. But we don't know what this height is, but we know that it has correlation with r. So oh yeah, it also has the angle of theta. So how to describe this r, how to describe this line is that this is also, this height is also the adjacent line of r. So it is r cosine theta. So the length of this line is r cosine theta because it is adjacent to theta and r. So because theta is adjacent to this line. So we can find that the potential energy is mgr cosine theta plus the kinetic energy, that is half times mv squared. So let's get back to here. So I'll draw it. So calculating it, we get phi is equal to square root of 2gr times 1 minus cosine theta. So it is the answer D. Number 2. Find the normal force acting from the hemisphere to the ball when the ball is on the hemisphere at the position described by the angle theta. So we find the normal force here of this ball. So first of all, the normal force is the force that is exerted by the surface on the ball. So that is the normal force. And the theory that you have to know is that when something moves or rotates something like a circle, it has a velocity here, but it also has the centripetal force towards the center, and the sum of all f that is radial. So it means that all of the forces that has the same direction or the same dimension as the radial here, or say basically the forces that is towards the center of the circle or to the outside of the circle. So f radial is just, so let's this, so there will be a circle. Wait. So there is a force centripetal. So there is a centripetal force. So the radial is that f. So let there be f1, f2, f3, and f4. So the f radial is f1, f3, and f2 because it has the same direction or the same dimension as towards the center of the circle. F4 does not because it is perpendicular or tangential to the circle. So I hope that makes sense. So let's get back. So the sum of f radial is equal to mv squared over r, and we take that the forces that is towards the circle is positive. And the other thing that you have to know is that when there is a vector, we can see it as the vertical component and the horizontal component. So when there is a theta here, the horizontal component that is adjacent to theta is phi cosine theta, and the opposite of the theta is f sine theta. So to find the normal force, let's get back to this drawing. So let's think of all the forces that is acting on the ball. So obviously there is the gravity, there is the weight, and there is also this is not a force, but let's write anyway. So there is a velocity, because like the ball moves like this, the velocity is tangential to the circle. It's always tangential to the circle, and until it uh, it doesn't move, at until it leaves the circle. And the other thing is that from the theory there is a centripetal force. So we take this direction as the positive direction of the sum of centripetal forces of the radial forces. And so as I said before, N normal force is the force that is exerted by the surface. So this will become important later. So let there be a normal force here that is always perpendicular to the surface. N and N is perpendicular to the surface. And mg can be described as this and this component, and we don't care about the horizon of the tangent component. We care about this towards or outwards the circle. So there is this vector because of mg. And what is mg? So how to describe this line? And to describe this line is that so because of this triangle, this is 90 degrees. So theta and this let's say alpha is equal to 90 degrees. So theta plus alpha is 90 degrees. So we know that because why is this 90 degrees? Because we know that this is 90 degrees too, and we know that the sum of all the angles of a triangle is 180 degrees. So theta plus this is 90 degrees plus something is under 80 degrees and something is alpha. So we know that this this is this is 90 degrees too. So from the fact that alpha plus theta is 90 degrees, we also know that this angle is alpha. So I hope that makes sense. So we can describe this line from this theta. So see that this line is adjacent to theta. So this is mg cosine theta. So we already know all of the forces that is acting on the ball. So from the theory we can describe that is the sum of the radial forces, and when we take this position as the positive direction, then we know that mg cosine theta is in the positive minus this, that is the normal force. So we can find n by this equation. So I'll redraw here. So we find this equation, and phi, we already know phi, and from number 1 we already know phi from number 1, that is square root of 2gr1 minus cosine theta. So we substitute phi, so it became this, and we calculate until it became this, where n is equal to 2mg 3 cosine theta minus 2. So the answer is E. So let's go to number 3. The position B at which the ball leaves the hemisphere is described by angle theta b. Find cosine theta b. So we need to know the condition which the ball leaves the hemisphere. So we know that N is the force that is exerted by the surface. So because there is something that is acting on the surface, there is N. So when ball leaves the hemisphere, means that it doesn't exert, so this ball doesn't exert anything on the surface anymore, so there is no, so the N is 0, so there is no N. So the condition of which the ball leaves the hemisphere is that the normal force is equal to 0. So we found N to this from number 2. And to mg we divide both of these to mg. This still becomes 0, this becomes 1. So 3 cosine theta minus 2 equals 0, and we find cosine theta is equal to 2 over 3, that is C. So number 4, find the speed of the ball immediately before the ball reaches the point C. So this is easy. So we can use the conservation of mechanical energy. So this ball from here to here has the same mechanical energy, and we already know that this point, the ball has mgr and no kinetic energy, so this mgr, and this point immediately before the ball reaches the point C is that the potential energy is 0, so there is no height above or below the ball, so the R is 0, so there is no potential energy. but there is a kinetic energy. There is a half mv squared of this ball, and we cancel m and move to here. We find phi is equal to square root of 2gr. That is the answer C. So number 5. Find the speed of the ball in the horizontal direction immediately before the ball reaches the point C. So this is the hardest part. So where do wait. So let's move to there. So we need to find the horizontal direction of the velocity when the ball leaves the hemisphere. So we need to think where is what is the direction of the velocity, and the velocity is the same as the direction of the velocity before it leaves the hemisphere, because let's think about it, and it's because when it leaves the hemisphere it has no reason for the phi moves to here, because the velocity is always tangent to the hemisphere, and when the ball reach there is no reason for the phi to change, because the direction of phi is only dependent on the tangent of the circle. But because it leaves the circle, it doesn't, or it has no reason to move here, so it has the same direction of when it leaves the hemisphere. And to find the phi x, so to find the horizontal component of the phi of the velocity is that, or maybe here. So let's draw this part again. So there is a angle theta to here. Wait. So let this be the angle, the theta b. And to find this angle, we know that this is alpha, right? You know this is alpha, and this is, and the v is always tangent to the circle, so it is always tangent to the line that is made up by the theta b at the theta. So this forms a 90 degrees. So this became, so a line, so angle of a line like this is 180 degrees. So alpha plus 90 degrees plus something is equal to 180 degrees, and we know that the something is theta, so this angle is theta. So this line is the adjacent of theta from phi, so we know that this horizontal component is v cosine theta, or to be specific, cosine theta b. Let's get back. So I'll draw this here, and we know that phi is cosine theta b, and we move cosine theta here, and we know phi from the number 1, these 2g are 1 minus cosine theta, and the from number 3, we know that cosine theta when it leaves the hemisphere is 2 over 3. So we write 2 over 3 and 2 over 3. 1 minus 2 over 3 is 1 over 3. So it became like this. And 2, so we express 2 as square root of 4. So square root of 4 times square root of 2 is 8, and square root of 9 times 3 is 27. So we know that the answer is E.